Welcome to week number 3 of Applied Food Science Lecture. It's me once again, Chris Potts, your food scientist. We have a little change of venue today, but nothing to be alarmed about. Now, this week we talked all about cooking methods and also the utensils that we use when we cook. Now, we'll get to cooking utensils later, but first I want to talk a little bit about what it means to actually cook food. Now, when you say cook food, the number one thing that most people think is, oh, I'm going to heat it up. Why is it that heating something up cooks the food? How does that change the flavor? Well, this actually goes back to something that was very important in the first chapter that you guys read, which is was the chemistry primer for this. And that was talking about energy and what sorts of energy are important in cooking. And one of those types of energy that's incredibly important is bond energy. And we're going to talk about why that's important today. The other type of energy that was really important is heat. Now, it really makes sense when we start thinking of putting those together, why they are important. So, one of the best examples of cooking, and one of the most basic things that we see when we cook foods, is the browning of foods. So why does that happen? Well, let's think back to last chapter. What are foods made of? They're primarily made of water, carbohydrates, proteins, and fats. Now, each of those react differently when you heat them up, and thus have a consequence on the flavor of the food at the end. One key molecule that we're concerned about, though, when we talk about heating foods is carbohydrates. Because when you heat carbohydrates, something very interesting happens. See, carbohydrates, as demonstrated by these nice, lovely Lego heads, are just chains of sugar molecules. Multiple sugar molecules attached to each other. They can be really long. They can be just a couple. They could be just one. This is glucose, okay? Now, here's the thing. When you start to heat up a carbohydrate, once you put in enough energy to break the bonds, i.e. the bond energy, interesting things happen. If we put in enough energy and these bonds break apart, these carbohydrates don't like to be alone. In fact, they undergo what is referred to as a combustion reaction. That's right, you're actually burning your food ever so slightly. And what's happening is the carbon within these carbohydrates is going to combine with oxygen that's just floating around. If you've ever heard that if you have a fire, it needs oxygen to survive. That's essentially what's going on here. We're burning the carbohydrates just a little bit, just a few of them. And what's happening is the carbon in there is combining with the oxygen, and we're getting whole new products in there that have wildly different flavors than the original carbohydrate. Now, if you want to see some of the molecules that we generate, you can check in your book on the 3rd page of chapter 14. There's a diagram of all the different compounds we can generate when you break down these carbohydrates into their carbons and combine them with the oxygen and other substances in the air. And that can be so delicious. It's a wonderful thing. That said, we can make it even better. Because a lot of times when we cook foods and we get browning, that's because the carbohydrates are cooking. Now, amino acids, which are similar to carbohydrates in that they're also chains of molecules, also have a similar bond energy to our carbohydrates. And that's great for us. Because if we cook and we can break apart the carbohydrates and at the same time break apart the amino acids, now we're essentially giving more playthings to our carbohydrates, and we can make much more complex structures and get new flavor compounds coming out of our food. This is referred to as the Maillard reaction, and it's essentially when you brown a food or caramelize it in the presence of amino acids. And what's beautiful about amino acids is they contain extra elements like phosphorus and nitrogen and sulfur. And these add an extra, most chefs refer to it as meatiness to our food that so many people the world over enjoy. In fact, Burger King's entire success can mainly be attributed to the fact that they char-broil their patties, giving them an extra bit of char, that Maillard reaction happening on the outside of their patties. Delicious. So, if cooking is all about taking these molecules and breaking them apart and then combining them with new other molecules to form these delicious extra flavor compounds, it does raise the question, how do you get that energy in there to break the bond in the first place? Now, we generally have three methods when it comes to cooking for breaking those bonds apart: conduction, convection, and radiation. So what's the difference? Well, conduction is the most direct heat source. That is when you have molecules and you apply the heat directly to them. You have other molecules that are hitting this and trying to break it apart. Direct examples of this, best known is grilling or sautéing. Anytime you cook on a surface, in a pan or on a grill, you have conduction. You are actually you are heating up these bars or this pan, and you're transferring the heat directly into these molecules and breaking them apart. Now, this is also where you get most browning of foods. Because that's such a high intensity energy transfer, it's much easier to break this guy apart by just pushing on him than it is by any other method. Now, our second method, convection, that has its own benefits. That's when we take molecules and we heat them up, but not the molecules that we want to eat. Usually this is water or air, and we heat them up and then we send them to surround the food and transfer their energy into the food. The most common way you can think about this is boiling a food. So let's say we've got our little bowl of water here. So we've got a bunch of water molecules. Let's say those are the tan ones. We've got some other things, some salt, some other flavorants in there. When we heat this up, remember, heating something is just making the molecules move faster. Now, if I took one of my molecules that I want to cook and I put it in there and then I shook this up, chances are it's going to break apart. That works great. Now, one of the beautiful things about this is that you're not just applying heat directly to these foods. You're giving energy to all the molecules around the foods, and then they're transferring the heat into your food. So oftentimes, boiling is a much softer cooking method. Same with baking. Baking is actually using the convection of the air to cook the food. Yes, the tray, the rack that you put the food on, there will be a little conduction there, but mainly it's the coils at the bottom heating air and then that air transferring energy in order to break these bonds and form new ones that does the cooking. Now, because it's a secondary transfer, it's a lot softer cooking. You're not going to get as harsh of a reaction going on. And while we treasure browning and the Maillard reaction, it can also be very nice to softly cook foods. For example, soufflés, also cooking vegetables. A lot of times, boiling those foods, it can bring out these extra flavors that were in there that are very subtle, and they can't withstand the intense energy that direct heat can bring. The other benefit to this is, especially when cooking with water, is water is very unique in that well, it's not unique. Liquids in general have a very unique property, and that's that if you boil them, that is to say get them up to 212 degrees Fahrenheit at sea level, again up here that's lower, we're about 2,000 feet above sea level, the water, the liquid, cannot get above its boiling point without vaporizing into steam. What that means is that if you've got water at a boil, all of the water in there is 212 degrees and cannot be higher. So if you are looking for an incredibly reliable thermostat to cook at, boiling water is a beautiful place to go because we know it will always be 212 degrees. While our grills and our stovetops and our ovens may be great places to really get that high heat, it's a lot harder to control the temperature because a lot of times they're 10, 15, even 25 degrees one way or the other from where they should be, whereas water will always and forever be a standard boiling temperature. Now you can alter it a little bit, adding salt here or there, but to put this old wives' tale to rest, if you wanted to raise the boiling point of your water by 1 degree, you would have to add almost a quart of sugar or salt to that water to get it to raise 1 degree. It's going to be some salty food. So how about our last method? That would be radiation. Now radiation, again, has its own benefits and some drawbacks. The idea behind radiation is that light, all the light that comes from the sun, or your lamps, or flashlights, or even the x-ray machines at the doctor, carries some energy with it. Those photons of light, these little, we can think of them as particles of light that fly through space at the speed of light, they carry some energy. And we can harness that energy to break the molecular bonds in food and cook. Now, microwave is hands down the most common form of radiation cooking. The great thing about microwaves is that microwaves are just the perfect wavelength, that is to say, they have a very specific energy. And what that means is that they're not going to bump into every molecule. Some molecules are way too small. And the light, the X-ray, the microwave, will go right around that molecule. One molecule it doesn't do that to is water. So when you cook in a microwave, essentially what you're doing is you're shooting these special waves into your food, and water is just the right size that it will hit these molecules and get them moving. And when they move, they're going to get the molecules around them moving. This is why it can be so helpful to cook veggies in the microwave, because they've got a very high water content. Whereas, say, if you took a piece of bread and put it in the microwave, wouldn't heat up so much, because the microwaves there's nothing for them to hit. There's no energy for them to transfer. All right? Also, a great reason if you ever heat up tea, or any sort of liquid in the microwave, it's very effective because the microwave is attuned just to that water molecule frequency. Now, that isn't to say it can't hit other molecules. One molecule that it's very attuned to can be ceramics. If you've ever had one of those mugs that you stick in there with some water or a bowl and you pull it out and the bowl is screaming hot, that's probably because it absorbed a lot of that energy. It's got the wrong sized molecules. So when they make microwave safe bowls, they look for molecules that these microwaves will pass right through and hit the water. Pretty neat. Now, here's the drawback to cooking with radiation, because microwave radiation isn't the only one. We can also use infrared, we can use visible light, but if we've got our food molecule, we now have nothing that's directly hitting this, no other molecule. So the best way to think about this is you're taking these little tiny things and you're throwing them at your food molecules. Which, it was probably not a very good example of me throwing that. Yes, it hit it. But consider, these are moving with the speed of light. So they've got a ton of energy to them. So if they hit, they're going to bring a lot of energy with them. The problem is, it's just not very many. and they're very far away. So infrared cooking can be wonderful because the infrared carries a lot of energy, but it doesn't go very deep. Infrared is different than microwaves. Microwaves are great because it goes really deep into the food. It gets all that water. Infrared, on the other hand, only hits molecules at the surface, which is great if you want like a sear on there because you're pounding these with a bunch of high energy molecules. They're breaking apart, but the inside is probably still going to be raw by the time the outside is charred. So a lot of times when using radiation as part of your cooking, you have to char it with the infrared and then finish it in the oven or something. So that's our types of energy. Now how do we get the energy, or how do we contain the food to get the energy to it? Well, the two types of utensil, that is to say cooking vessel, that we traditionally use in the kitchen are ceramics and metals. Now, metals, by definition, are anything to the left of the staircase on the periodic table. If you're confused what that is, type in metals periodic table on Google and you will be able to see very clearly there's this nice little staircase on there. Everything to the left of that is a metal. So most of the atoms on Earth are metals, and we can use them in a huge variety of ways, and they all have similar properties. You know, they're very shiny traditionally. They're what we call malleable and ductile. That is to say, if I hit this with a hammer, it would dent. It wouldn't crack. And other than those, they can conduct electricity, they conduct heat really well, but beyond that, there's not a lot all of them have in common. So there's a huge variety of metals. Ceramics, on the other hand, ceramics are traditionally made of non-metals. Now, non-metals is everything else in the periodic table, which doesn't amount to very much. But we can combine them in a large variety of ways, and we can get things like porcelain, we can get glass, we can get Pyrex, all of these different materials that have slightly different properties. So what does this mean when it comes to cooking? Well, traditionally, we call these by two very different words. This is what we call a conductor, and this is what we call an insulator. What does that mean? Well, let's start with the insulator. The idea behind an insulator is that all the molecules that make this up are very sturdy and they're very rigid. And so think of them like the British Royal Guard, right? They stand tall, they stand there, they do their job. You can go up to them, you can poke them, you can prod them, you can put a whole bunch of energy into this, and they're not going to move a whole lot unless you really go at them. Okay? So these rigid molecules might not seem great for cooking because they don't put heat into the food very well. But again, consider there are different ways we want to cook. Ceramics are wonderful if you want a softer cooking. That is to say, you don't want as much browning on the outsides. Think of if you've ever made a custard or a creme brulee in one of these. While the top might get a little brown, on the sides, it's still custardy. There's no browning reaction that happens there, which can be wonderful. You don't want crunchy custard? Ew. Now, on the other hand, we've got our metals. Now, metals are what we call really good conductors. And what that means is that the metal molecules, the metal atoms that are in here are very loosey-goosey, right? They're just hanging out, whatever, man. And if you hit them with energy, they're just going to pass it on, right? Which is awesome if you want to get heat into your food. If you take one of these and you crank up the heat on your stove, and then you throw a carrot in there, it's going to brown really fast. In fact, it'll probably burn almost as soon as it browns because this is conducting so much heat. Now, that's wonderful. Again, if you want to put a lot of heat into your food. But here's the problem. Because these metals are transferring heat so quickly, they don't heat very evenly. Now what you'll notice about this pan it actually has this extra alloy layer on the bottom. Now, what's neat about metals is that they're not very picky about who they're around. And so you can make alloys, that is to say, a mixture of more than one metal, to increase and decrease different properties. Now, this is mostly stainless steel. That's iron with a little bit of zinc in it, which is great because, well, it's stainless. It doesn't rust, even though it's mostly iron. It's very hard. It's durable. It's got really good conduction to the food that it transfers that to. Stainless steel, it's non-reactive. That is to say, it doesn't. These loosey-goosey metal atoms don't come off into your food. That wouldn't be good. Stainless steel is wonderful, but it doesn't spread out the heat very well. So if you put this pan half on your burner, only half of the food would cook. If this was just straight stainless steel. Now, there is an alloy here that's got extra molecules in there that increase the insulation properties of this bottom. Now, what that does, you might be like, I don't want an insulator on the bottom of my pan. Yes, you do, and don't you forget it, because an insulator will spread the heat out evenly before transferring it to the stainless steel of this pan and give you a really nice, even cooking. Okay, now real quick about a couple of our different metal types, which each have their pluses and their minuses. Okay, we have these. We have some copper. Copper was for a really long time a really popular cooking metal because it heats up fairly evenly. It's a really good conductor. In fact, it's widely considered the best cooking conductor that there is. It conducts heat better than anything else. The problem, though, is because it's such a good conductor, the molecules are so loosey-goosey that when you cook with copper, often the copper atoms can actually kind of fall off and incorporate into your food, into whatever you're cooking. This can actually be good sometimes. There have been studies that show that when you whip egg whites in a copper bowl, the copper ions coming off of that bowl and into the egg whites can actually act as a stabilizing element. Now that's great, and a little bit of copper won't hurt you. But in the long run, if you're only using copper and you're using it very heavily, it can have some adverse health effects. So usually copper is only used for bowls, measuring tools, very rarely anymore used as a main cooking pan. Now we also have the almighty aluminum. Now, aluminum is wonderful. It's the second best conductor in all the metals that we use to cook with. Not only that, but aluminum foil is incredibly versatile in that it's a great conductor of heat, but it's also incredibly malleable, right? We can move it, we can bend it, and it won't break. And that's wonderful for covering foods, and even for using in bowls, in cooking sheets, cookie sheets. Again, because this can change a lot. It can change shape in the oven without breaking, without being permanently harmed, and it conducts heat really, really well. So in a convection environment where you have a very even spread of heat around the pan, it works wonderfully. That said, because it is so malleable, making a pot like this out of aluminum would just lead to dents and deformations. Now, our final type of cooking metal that you see a lot is cast iron. Now, iron is a wonderful conductor. Not as good as copper or aluminum, but it's pretty good. Now, the thing about cast iron is that these things are heavy. We actually take iron and we infuse them with some carbon. Now, if you know anything about the periodic table, carbon is actually a non-metal. That is to say, it is an insulator. What that does is it increases the insulation properties of this, meaning that the heat is going to spread really evenly through the cast iron skillet. If you have one of these with a short handle like I do, you know how hot that thing can get because the heat is going through the entire pan. At the same time, iron is a great conductor, meaning a lot of the heat gets to the food. That's wonderful. Here's the problem. These things have a tendency to rust. You can actually see I've got a little on the bottom of my pan that I need to get after with some steel wool. Now the problem, or one of the solutions that people have found is they'll actually what is called cure their cast iron skillets. What this means is you put a layer of fat around the cast iron skillet and then you heat it up, really high heat for hours. Don't do this inside, please. And before, if you have a cast iron skillet, usually people say to cure it about once a year. That's a good amount. And what that does is when you heat up this metal, essentially all the atoms that make it up start to heat up. That means they're moving more. That creates these little tiny cracks in between the atoms because they're all spreading out. They've got so much energy. And then the fat, with either an oil or lard is my personal choice, maybe some Crisco. It allows those to go into the metal. And like we learned last lecture, fat and water don't mix. So once you heat this and you incorporate that fat into here, you let it cool down, that fat is going to be in the metal. And what that does is it creates this nice waterproof seal over your cast iron that lets you cook with it without having to worry too much about rust, which is very nice. Not to mention, some people say that curing process can actually add a lot of flavor to the foods that you cook, which is all quite wonderful. Now, one thing that I didn't talk about with ceramics that I just want to touch on real quick, one of the other great benefits to ceramics is because the molecules in here are so rigid, they don't impart any flavors, additional flavors or additional molecules into the food that you cook inside of them. That can be very handy. Now, with that said, thank you for listening. Next week, we will be talking about the magic of the dairy world. Keep an eye out for the bonus bit. That's where your lab instructions will be. Thanks for watching.